All right, so in section 3.1, we covered a few different techniques for differentiating functions, and these were shortcuts that allow us to bypass that limit definition that we talked about at the end of chapter 2. The types of techniques that we're talking about here in chapter 3, these shortcuts, fall into two different categories. So there's techniques for differentiating specific types or classes of functions, and so far the specific types of functions we've talked about have been constant functions, power functions, and exponential functions. And then we talked about some other differentiation rules which apply to more general types of functions, and those were the constant multiple rule and the sum and difference rules. And in those, the way that you know that we're talking about more general types of functions is in the statement of that of those theorems or those rules. It'll say f of x and g of x, things like that. It won't say, that we're dealing specifically with an exponential function or specifically with a polynomial or something like that. And throughout this first half of chapter 3, we're going to continue building on these. We're going to continue talking about these rules for specific functions and rules for kind of general ways of combining functions with addition, subtraction, multiplication, division, that kind of stuff. In this section, we're going to be addressing two specific rules that fall into that second category, general functions. And these deal with how to differentiate a product of two functions and also how to differentiate a quotient of two functions. Now, the reason we didn't talk about these in the previous section in 3.1 is because these rules don't work the way that you might expect them to. So when we talked about, for example, differentiating a sum of two functions, the derivative of f of x plus g of x is just equal to the derivative of f of x plus the derivative of g of x. It corresponds in a very similar way to the same limit law that we learned in 2.3. The limit as x approaches a of a sum of two functions can be evaluated by taking the limit as x approaches a of each function individually and then adding the results. I even mentioned back then it's kind of like almost like a distributive property, even though technically that's not what's going on there. So based on what we have seen so far, it's tempting to think that when dealing with a product of two functions, so f of x times g of x, it's tempting to think that the derivative of this is just the product of the derivatives. But this turns out to be false, even though we have a limit law that would suggest that something like this is true, at least in the case of limits. So to illustrate why this doesn't actually work the way you might expect it to, let's take a derivative of a function that we already know how to deal with. F of x equals x squared. So from our power rule that we talked about in 3.1, we already know that if f of x equals x squared, then f prime is equal to 2x. Okay, but what if we took the same function and tried to approach it differently? What if we rewrote x squared as x times x? Now I'm representing this as a product of two functions, and if this differentiation technique actually worked, then what I should be able to do is take the derivative of this x and the derivative of this x separately and multiply the results, which I'm trying to do down here. But notice when we do that, the derivative of x is 1, and same here. The derivative of this x is also 1. 1 times 1 is 1, not 2x. I don't get the answer that I should be getting by using this technique. Therefore, this does not work, okay? Fortunately, there is a way of dealing with a derivative of a product of two differentiable functions. It just looks different. It looks a little bit more complicated than this. And so what we're going to do down here is derive it. I know this looks like a lot right here, but this is just a proof. You're not going to be asked to reproduce this. I do, however, want you to understand each step of what's going on here. So again, our goal is to try and take the derivative of f of x times g of x, where f and g are both differentiable functions, meaning that this would exist in the first place. Or at least the derivative of f and g independently should exist. So going straight to our definition of a derivative, because we're differentiating a product, then the functions up here should look like that product. So f of x plus h times g of x plus h minus f of x times g of x all over h, and we take the limit as h goes to 0. So getting from this step to this step is not intuitive, because what we're doing is something that I've mentioned before. We are starting by making this expression more complicated, specifically by adding a quantity and then subtracting that quantity away. Right here in the middle of this numerator are the quantities I'm talking about. We're actually starting with a subtraction step. So here, f of x plus h, g of x plus h, the same thing I had up here, nothing has changed there. I'm subtracting g of x times f of x plus h, and then adding that same thing back again, plus g of x times f of x plus h. So, and then I have this minus f of x, g of x here. So if I wanted to go back a step, these two things would end up canceling each other out, which shows me that it's equal to this. So by adding and subtracting the same number, I haven't actually changed anything. I've only changed the way that this looks. Now that might seem a little bit bizarre. Why would you add and subtract this specific quantity? It doesn't seem like a natural thing to do. But now that I have done that, there's some simplification that can take place. So the first thing I'm going to do is notice that in my first two terms here, I have f of x plus h showing up. So I could factor that out. And notice the g of x plus h minus g of x is what's left there. Similarly, on this side, I have a common factor of g of x. So if I grouped up these first two terms, factored the g of x out, I would have g of x times f of x plus h minus f of x. The next thing I'm going to do is take this plus here and use it to split this up into a sum of two rational expressions, two quotients. And I'm also going to take the thing that I factored out of each pair of terms up here and just bring it all the way out to the front of that rational expression. So I'm going to have g of x plus h minus g of x over h, which you're seeing here. And then the f of x plus h is going to be brought out to the front of that quotient. These are all valid algebraic steps that we could be doing. Similar here, I'm going to bring the g of x out front, and then I'm left with f of x plus h minus f of x over h. So you notice the two quotients that are left here look like difference quotients. And what I have is a product of a couple of things and a sum of those things. So using my limit laws, I can bring that limit into each term of the sum, and then bring that limit also into each factor of each product in that sum. So that gives me these four limits here, okay? Now, two of these limits are going to give me derivatives. Notice the limit as h approaches 0 of this difference quotient, by definition, is g prime of x, and we're allowed to go from here to here because we assumed at the very beginning that g is differentiable. Remember, that just means that this exists and is equal to g prime. Similar here, this limit of this difference quotient will give me f prime of x. This guy right here, this g of x, remember, there's no h showing up anywhere in this thing. So even though it is a function, it's a function of x, whereas our limit deals with the variable h. So because there's no h appearing in this expression, it gets treated like a constant. And the limit as h approaches anything of a constant would be that same constant, or in this case, this same function of x, g of x. This one is a tad more complicated. The limit as h approaches 0 of f of x plus h is equal to f of x. And I'm going to walk through this little argument down here to show why this limit is equal to this one. But this is the thing that we're going to use for products of functions. We call this our product rule, and I'm going to state it again down below. If you want to take the derivative of a product of two functions, f times g, then the derivative is equal to the first function times the derivative of the second, plus the second times the derivative of the first. Okay, and because this is plus, we could rearrange these terms using the commutative property, and I could instead do the second times the derivative of the first and the first times the derivative of the second in that order. It doesn't matter because, again, you can add this in whichever order you want. Let me quickly address this step here, getting from the limit as h approaches 0 of f of x plus h to f of x. Okay, now it might at first seem obvious that this is true, but depending on the function f of x, if f of x has no conditions that are placed on it, this is not necessarily true. So to give you an example, let's suppose that this is f of x, right here. Let me call this x right here, and let's say that this is x plus h, okay, which makes this h. All right, so the limit as h approaches 0 of this expression, if I go up here, this guy right here is f of x plus h, right? As I allow h to shrink to 0, what's happening is x plus h is becoming closer and closer to x. So another way of thinking of this is I'm taking the limit as my independent variable approaches this x right here. Now I can see in this case that the limit as h approaches 0 of f of x plus h should be approaching this value right here. But my f of x, the actual value that my function takes on, is not there. It's up here, okay? So in a case like this, this step would not be valid. The limit as h approaches 0 of f of x plus h would not be approaching f of x. But I know that I'm not dealing with a case like this because what's happening here is I have a discontinuity at x, right? And even though we didn't state explicitly that f of x is a continuous function, we did state that it's differentiable. And if a function is differentiable, as we proved back in chapter 2, that implies that it's also continuous. So we wouldn't have a case like this occurring with this function f. To ensure that this step is in fact accurate, though, I made a little argument here using the definition of continuity. So again, we're trying to prove that this is true. The limit as h approaches 0 of f of x plus h equals f of x. And knowing that f is continuous based on what I just said a second ago, we're going to make a variable substitution. If I set x plus h, the thing inside parentheses here, equal to some other variable y, then I could solve this for x so that x is equal to y minus h. Now, if I let y approach x, or sorry, if I let h approach 0 here, then this side is going to y, which is equal to x. So I can see that y is approaching x. Or I can see that more clearly here. As h approaches 0, y is approaching x. So making some substitutions, the limit as h approaches 0 of f of x plus h, this limit can be reframed this way. The limit as y approaches x of f of y, because x plus h was defined to be equal to y. And as we already said, we have continuity in this function. So by the definition of continuity, the limit as x approaches x, as the limit as y approaches x of f of y is equal to f of x. So that establishes that this thing is equal to this thing, which is exactly what we were doing in that step. Okay? So that's a whole lot of talk about this proof. Your book walks through a different proof of the product rule using a nice visual, using rectangles. And I encourage you to read that one too. Go to your book in section 3.2 and look at the way that it proves it, because it's a really good perspective to have. I just wanted to offer something different, something using the definition of the derivative as we've seen it so far. Okay? So here's a restatement of that product rule using a different notation. But again, the derivative with respect to x of f of x times g of x is equal to f times the derivative of g plus g times the derivative of f. Now this notation is cumbersome to work with. And so oftentimes when we're dealing with the product rule, and again, as we'll see later, the quotient rule, we use variable notation. So if I let f of x equal u, so I'm thinking of u as a dependent variable for this function, and if I let g of x equal v, then the product rule can be stated in this slightly less cumbersome way. The derivative of u times v, so the derivative of the product, or I can also think of that as uv prime, is equal to uv prime plus vu prime. So the first times the derivative of the second plus the second times the derivative of the first. All right, here's an example. So I want to evaluate the derivative of e to the x times 4x squared minus root x. And I can see from this I have a product of two functions. So using my product rule, this is going to be equal to the first function times the derivative of the second. So that's u, and that's v, meaning u would just be e to the x. V prime means the derivative of this second function. So I take the derivative here using my power rule. 4x squared, that's going to become 8x. Remember, the square root of x can be written as x to the 1/2 power. And using my power rule, that becomes 1/2 x to the negative 1/2 power. I'm going to choose to not rewrite that in radicals, even though there would be no issue if I did choose to do that. Then I need v times u prime. Well, I'm going to write u prime first because v is a more complicated function. I like having the simpler thing out front like this. If u is equal to e to the x, then u prime is also equal to e to the x because we know that e to the x is its own derivative. That's what we talked about at the end of section 3.1. Times v, so this function here, 4x squared minus root x. I'll just call it x to the 1/2. Now I could leave my answer in this form, but as we're going to see a little bit later on in the course, specifically towards like chapter 4, in chapter 4 when we're dealing with optimization and stuff like that, usually taking a derivative of a function is just one of the first steps in a problem, and then there's more things that happen after that. And a lot of the time, when we're doing some of the applications of derivatives later, we're going to be taking our derivative, setting it equal to 0, and then solving the resulting equation. So for that reason, oftentimes when I take derivatives, I'm going to do an additional step where I try and factor or simplify, because that's going to help in solving those equations that come later on in the course. And in this case, I could see that I could factor an e to the x out. Okay, leaving me with these 4 terms here, none of which are like terms, so I can't combine any of them, but I am going to write them in like descending order according to their exponents. So plus 8x minus 1/2. Well, I did this in the wrong order, but that's okay. 1/2 x to the negative 1/2 power minus x to the 1/2 power. I meant to put these in different order, but it's not wrong the way that I've written it. Okay, so again, even though this answer is totally right, this step right here is absolutely right, and there's nothing incorrect about what I wrote here, I prefer to factor my answer because I know that in a future problem, this is going to be more useful than that. Okay, let's take a look at another example. Let's let g be a differentiable function, and f of x we're going to define in terms of g of x. F of x is equal to x squared times g of x. And we have a little bit of information about g of x as well. G of 3 equals 1, and g prime of 3 is equal to 4. We are asked to find f prime of 3. Notice that nowhere am I given I'm not given the form of g anywhere. I'm not told whether g is a polynomial, exponential function, or some combination of those things, or something entirely different. We're just told that it's differentiable, and I have a little bit of information about it. So we have to work with what we have. If f of x is equal to this, then what can I say about f prime of x? Well, that's the derivative of x squared times g of x. But now I can see that I'm looking at the derivative of a product of 2 functions. So I would be using my product rule. This is equal to the first function, x squared, times the derivative of the second function, g prime of x. That's the best I can do because I don't know what g of x looks like. I could just write g prime. Plus, I'm going to do it this way, the derivative of the first function, 2x, times the second function, g of x. Okay? So again, I don't have enough information to get any more specific than this. But fortunately, that doesn't matter because I have enough information to find the specific function value I'm looking for. F prime of 3 is the same thing as plugging 3 in to this right-hand side. 3 squared times g prime of 3 plus 2 times 3 times g of 3. Okay? Now, I can work this out. 3 squared is 9. G prime of 3 was given to me up here. It's equal to 4 times 4. 2 times 3 is 6. G of 3 was also given to me up here. G of 3 is equal to 1. So this becomes 6 times 1. And now what do we have? 9 times 4, which is 36, plus 6 would be 42. Okay? So you'll see a problem or two like that in the homework where, you may not have all of the information that you might want about G, but you do have enough to answer what the question is asking you. Let's go ahead and stop this section here, and we'll get into the quotient rule in the next part.